In our definitions of the trigonometry functions, we considered a unit circle, and a point on that circle, when joined by a straight line to the origin, defines an angle between the positive x-axis and that line. We called the sine of that angle the length of the vertical line in that triangle. We'll illustrate that line in blue to make it stand out. We want to see the pattern of how that sine changes as the angle increases from 0 all the way around to 360. Let's reset it to 0. And we want to see what the graph would look like if we plot on the horizontal axis our angle x and on our vertical axis the value of the sine of x. Let's bring in a separate graph so we can see these both at the same time. As our angle increases from 0 to 90, the value of the sine increases from 0 to 1. And at first, although it looks like it's almost going up in a straight line, we can see that the increase in the angle is not linear. It curves off nicely as we head towards 90. Let's now let the angle increase from 90 to 180. It's easy to see we're going to get the mirror image as the height decreases to 0. If we now go from 180 to 270, we'll see the same thing but with negative values of sine, as the line is now underneath the x-axis, with a maximum value when we get to 270 of -1. If we now allow that angle to increase to 360, the curve completes back to a value of 0 when we get to 360. So for angles in between 0 degrees and 360 degrees, this is a graph of sine x. Here is that same graph, but zoomed out so we can see a larger range of values for x. Now there's no reason why we need to stop when we reach 360 degrees. We can carry on turning our point around and around again on the circle. So once we've reached 360, if we carry on turning around, we have turned through an angle of 360 plus a bit more. And because that point is just going to go around the circle again and again, it's easy to see that the graph is just going to repeat itself. So we'll have this pattern as we turn further and further around in the anti-clockwise direction. But there is also no reason why we only have to turn in an anti-clockwise direction. That's our convention for having positive angles. That means that if we turn in a clockwise direction, we'll have a negative angle. So for negative values of x, the graph will continue in this fashion. The picture we are establishing is a graph of y equals sine x for any value of x. By considering that graph we have shown, we can see the following properties of the sine function. It is defined for all values of x. We will always be able to find a value for the sine by considering how far around the circle we have turned. This function has periodicity, which means that it repeats. If we take the basic portion as being the piece from 0 to 360 degrees, we can see that after that the same pattern will repeat again and again. We say that its period is 360 degrees because that's the basic unit we need to keep repeating. The values that the sine function can take will always be between -1 and 1 because our blue line in the triangle can only go up to a maximum height of 1 and down to a maximum depth of -1. By looking at our graph, we can see that the value of sine of x will be 0, in other words where the graph crosses the x-axis, for every multiple of 180 degrees. So 180n degrees, where n is an integer, positive, negative, or 0. For example, when n is 0, we have the x of 0, where the graph does indeed cross the axis. When n is 1, we'll have 180 degrees. When n is 2, we'll have 360. When n is -1, we'll have -180. These are all the points where the value of sine is 0. We can see from inspection of the graph where the value of sine x is +1. That's going to be at 90 degrees, and because of the periodicity of the function, that will repeat itself as many 360s as we would like to add on. So if we add on 360n, where n is again an integer, we'll find another point where the value of sine is 1. Similarly, the value of sine will be -1 at 270, plus as many 360s as we like. Returning to our trigonometry definitions, we called the cosine of x the length of the horizontal line in that right-angled triangle. Colouring that red for emphasis, we'll now be interested in how the value of the cosine of x changes as x changes. First of all, just from 0 up to 360 degrees. Let's reset that angle to 0. And now we want to consider a graph of how the length of that horizontal line changes as the angle changes. Well, when we have an angle of 0, you can see the length of that horizontal line is 1. If we let that angle increase from 0 to 90, then the length of that line goes from 1 all the way down to 0. So similarly to the sine curve, we have a graph which mostly looks like it's nearly a straight line, but the ends of it show that it curves. But instead of going from 0 to 1, it's going from a value of 1 to 0. If we now let the angle increase from 90 to 180, the line will go from a length of 0 to negative 1, because now it is pointing in the negative x-axis direction. If we increase from 180 to 270, the line will return to a length of 0, but still having negative values. And from 270 to 360, the length increases from 0 back to 1. So our basic portion of a cosine graph is very similar to a sine graph, but not quite in the same position. Here is our zoomed out version. We can see what would happen if we carry on turning around that circle and have angles larger than 360. Once again, the graph will repeat this basic shape forever. For whatever our large values of x, we'll always be able to find a value for cosine x. And also, if we consider negative angles turning clockwise, the graph will repeat in the other direction. So, we now have a graph of y is equal to the cosine of x. We can use our graph to see the following properties of cosine. The cosine function is defined for all values of x. The periodicity of cosine is 360 degrees. The graph always repeats after that interval. The value of cosine is always between negative 1 and 1, because the length of that horizontal line will always be between negative 1 and 1. The cosine function has a value of 0 at 90 degrees. We can see it crosses the axis there, and then crosses the axis again if we add any integer multiple of 180 degrees, positive, negative, or 0. The cosine graph has a value of 1 at every integer multiple of 360 degrees, whether that integer is positive, negative, or 0, and has a value of negative 1 at 180 degrees plus any integer multiple of 360 degrees. Our definition of the tangent of the angle x was the gradient of the hypotenuse of this triangle. We'll illustrate that by making the line green to stand out. Let's reset the angle to 0 and consider the value of the tangent of x as that angle changes from 0 to 360. When the angle is 0 degrees, the gradient of that line is 0, and so the tangent of 0 will be 0. As the angle increases from 0 to 90, the value of the gradient increases until when we get to 90 degrees, the line is pointing straight up. Its gradient is undefined, because we will be dividing the change in y, which is 1, by the change in x, which is 0. So the tangent function is not actually defined for a value of 90 degrees. As we increase the angle from 90 to 180, the line now has a negative gradient, which starts off being very large and comes back down to 0 when we get to 180 degrees. And from this point on, the pattern is going to repeat. As we increase the angle from 180 to 270, the gradient is again positive, increasing to an undefined value when we get to 270. From 270 to 360, the gradient is again negative, returning to 0 when we get to 360 degrees. Here is our zoomed out version of that graph. As we've noted, tangent is not defined when x is 90 degrees. If we draw in a vertical line at this point, we can see that this is an asymptote to the graph. The curve gets closer and closer to this line as we approach 90 degrees from below, and also as we approach 90 degrees from above. In the former case, it approaches the line in the positive y direction, in the latter in the negative y direction. We could also repeat this line for x is equal to 270 degrees. If we now consider what happens for angles greater than 360 degrees, so the point keeps moving around the circle defining larger angles, we will see again that this pattern is just going to repeat. Similarly, we could consider what happens if we wind round the circle in the other direction, defining negative angles. The pattern will repeat for values of x less than 0. And these asymptotes will also repeat every 180 degrees, either in the positive direction, but also in the negative direction. If you are trying to draw a graph of the tangent function, it is a very good idea to draw the asymptotes before you try drawing the curve. Also note that as the curve crosses the axis, for example at 0 degrees, the gradient of the curve is non-zero. This curve does not sort of level off and then go back up. It crosses through the axis with a non-zero gradient. So these are the properties of the tangent function. It is defined for every value of x except for 90 degrees plus any integer multiple of 180 degrees. These are the angles for which the hypotenuse of that triangle would be pointing straight up and therefore does not have a finite value. Tangent has a periodicity of 180 degrees, that's how often it repeats. The tangent function can take all values. There is no upper or lower limit to the gradient of that hypotenuse, and therefore there's no upper or lower limit to the values that tangent can take. The tangent function has a value of 0 for every integer multiple of 180 degrees. So, for example, when x is 0, 180, 360, negative 180, these are the places where the tangent curve crosses the x-axis. And the tangent graph has vertical asymptotes. The equations of these asymptotes are x is 90 degrees plus any integer multiple of 180 degrees. These are the same values for which the tangent function is undefined.